Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is going to be lecture number 52 and this is tutorial 14. So in the previous tutorial and lecture, we were discussing about the partition function, right? And I had made a statement, that is statement Z. I'm just writing it down for your clarity here. So statement Z, ST, referring to statement Z means that I'm talking about the Z, that is the partition function, being a measure of the number of thermally accessible states at any given temperature. Okay, right? So the place where we stopped, the juncture where we stopped in the previous lecture was that we had to justify the statement. So to justify the statement, we were considering the extreme cases. That is the case where in the expression for the partition function, this term beta tends to infinity, that is my temperature tends to 0, and my beta tends to 0 and my temperature tends to infinity. Now let us consider the case 1 first. Case 1 is where my beta tends to infinity. Now let's just expand this to just containing 2 or 3 terms. For example, Z, let's say is given by e to the power minus beta E naught plus e to the power minus beta E1 plus e to the power minus beta E2 plus blah 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 dot dot dot. Okay, right? We know that here my mod E naught is less than mod E1, which is less than my mod E2, etc., right? Because this is the lowest energy state. We start from the state I equals 0, that is E naught, which is the ground state for the system, right? So because this is e to the power minus beta E naught, this condition is always going to be there. Now, as beta tends to infinity, right? So as beta tends to infinity, what happens to this thing? I'm talking about e to the power minus something very large, e to the power minus ax, okay, right? Where this is a, let's say this is a, and beta is my x, and my x tends to be very large. E to the power minus ax is first of all a decaying function, correct? So therefore, as beta tends to infinity, all of these terms will tend to 0, correct? All these terms will tend to 0, because this is also of the form e to the power minus a1x, this is of the form e to the power minus a2x, e to the power minus a3x, etc. Okay, so as beta tends to infinity, note that all terms in Z will tend to 0. But there is a very crucial difference here. Okay, it is that because of this idea, because of the fact that my E naught is the lowest value of the energy, right? Because my mod E naught is the lowest value of the energy, this term, right? This term E naught, I mean this first term, right? Let me just call this T1, T2, blah blah blah. Okay, right? This is T2, T3, and so on and so forth. Okay, right? But because my E naught, modulus of E naught is less than modulus of E1, because of this condition, my T1, right, will go to 0 the slowest. Please notice, this is a very important point. Okay, right? Now, because my T1 will go to 0 the slowest, vis-a-vis the other terms. Okay, right? See, because this is a larger number than this, right? And this is a larger number than this, right? As this becomes, as beta tends to be infinity, right? As beta tends to be very large, in other words, right? You're multiplying this term with this very large term, and this is a larger number, right? And owing to this negative sign also, this approaches 0 much faster than this term. Are we all good? Okay, right? So effectively, what's happening is that as beta tends to 0, my Z, okay, right, can be approximated as only this term, e to the power minus beta E naught. Are we clear? Because of course, every term will approach 0, but the rest of the terms will approach 0 faster than the first term. So therefore, only my T1 is going to be surviving. Okay. Now that I have my beta tends to 0, my Z is this. What is my expression for the Boltzmann distribution? My Ni by N is therefore, as beta tends to 0, under this condition, okay, my Ni by N is going to be e to the power minus, well, we only have one state left here, e to the power minus beta E naught divided by e to the power minus beta E naught, right? Which is going to be my I equal to 0 here, right? Which implies that this is of course equal to 1. I mean, this is 1, which means that my N naught equal to N. Correct? My N naught is equal to N. And what is the meaning of that? Well, this implies that at very low temperatures, right? That is, this beta tends to infinity. My apologies, okay? As beta tends to infinity and T tends to 0. Oops, okay. So we are discussing the case beta tends to infinity. I momentarily made a small mistake. So as beta tends to infinity, as my T tends to 0, this case will be holding good. Okay. Now as this case is going to be holding good, my N naught by capital N will be 1. What is the physical implication? At low temperature, only the ground energy state will be occupied. Please note this point, okay, right? This is extremely important. So at very low temperatures, especially as T tends to 0, right, only the ground energy state will be occupied because my N naught equal to N. Because as T tends to 0, only one term here survives in this summation, because that tends to go to 0 the slowest. So therefore my N naught by capital N is going to be 1. All good? So this is the implication, and we saw by discussing this extreme case, that is of like beta tends to infinity and T tends to 0, that all the molecule, this is intuitive, right? All the molecule, when we're talking about very low temperatures, they're going to be lying in their ground energy state. This also gives us an indication that, hey, indeed, my Z is a measure of thermally accessible state at T tends to 0. Okay. Now what do we do next? We shall now go to the next extreme case. But before going to the next extreme case, I will just highlight to you one more beautiful aspect at low temperature itself. Okay. Let us continue to stay in the realm of T tends to 0 and beta tends to infinity for just a few seconds longer, right? And we shall then go to T tends to infinity case. Okay. So you see, staying with T tends to 0, now that is beta tends to infinity. Recall from lecture 12, okay? Not lecture, tutorial 12, sorry. From T12 towards the end of the tutorial 12, okay, right? End part. I mean, that is the concluding part, being colloquial, okay, right? If you look at the end part of it, I had given you the expression that my Ni by N, which is equal to e to the power minus beta Ei divided by sigma over I equal to 0 to whatever states, e to the power minus beta Ei, can also be written as, again, Ni by N, which is equal to Gi, where G is the degeneracy of the system now, okay, times e to the power minus beta Ei by sigma I equal to 0, e to the power minus beta Ei. Now please note this point here. Here the summation is over the degenerate states, okay? So here the summation is over degenerate states. I told you that this could be easily written as this, but I again emphasize, did not derive it, okay? I just told you this could be done. It's a very one or two step process, but because we have to discuss so many more things, I'll leave it at this, okay? So note did not derive. I just told you. Now, if you consider this particular expression, okay, right? If you consider this particular expression and we use the same idea, that is at low temperature, only the ground energy state is going to be occupied, just like my N naught is equal to N, right? By N is equal to 1 in this case, right? So therefore, my N naught is equal to N. That is what we saw by using this version. By using this equation, we shall be getting, okay? We shall be getting that my denominator is this one, right? This particular term, that is Z here, right? What are we looking at? Just like, by using this equation, let's call this the Boltzmann distribution without degeneracy. This is simply Boltzmann distribution, and let's call this the Boltzmann distribution including degeneracy, okay? Now, from the Boltzmann distribution, we got this, okay? Now, while using the same idea that T tends to 0, that is beta tends to infinity, using this Boltzmann distribution including degeneracies, we get, okay, it is very easy to show that, okay, right, that my Z, which is equal to sigma over I equal to 0 to whatever thing, right, my beta EI is equal to G naught. So in other words, right, only the first term would survive, right? Only the first term would survive in the case of using this expression, okay? So it is by using the same math, it is easy to show that my Z equal to G naught when I express my Boltzmann distribution, using in terms of degeneracies, okay? Now, this implies that, again, at low temperature, that is like as T tends to 0, right, my partition function, my Z, right, is a measure of the ground state degeneracy, okay? Is a measure of ground state, I'll just put it G, okay, right? Is a measure of my ground state degeneracy. Just note this point, okay? I mean, it is just 1 or 2 steps, to go from there to here. I'll give it to you as a homework because I want to discuss many more things in this tutorial, okay? But it's very easy to show this, all right? So please note. So what did we do? What did we do so far here? What we did was I showed you the relevance of the partition function by considering the case of T tending to 0. And I also showed to you that when we consider the Boltzmann distribution expressed in terms of degeneracies, right, it can be shown that my partition function is equal to the degeneracy of the ground state as T tends to 0, okay? So this is all I wanted to convey to you by discussing the T tends to 0 case. Now let's consider the T tends to infinity case. For fun, right, I'll use this equation now. Instead of using the original Boltzmann equation, I'll use the Boltzmann distribution in terms of the degeneracies, okay? Now, and let's consider the T tends to infinity case. So now you just consider this equation, that is the Boltzmann distribution expressed in terms of the degeneracies, and let's say I consider the case, say, T tends to infinity and beta tends to 0, right? Now if you take a look at this particular equation, what happens to my numerator? My Ni by N in that case, right, will become, what happens to the numerator? Well, this tends to 0, so therefore my numerator is going to be 1, okay, right? E to the power minus 0, I mean e to the power, anything to the base to the power 0, right, any real number, right? So that is going to be, this is therefore going to be 1, right? And what about the denominator? Well, it's going to be a series of 1s, right? Well, for I equal to 0 state, 1, I equal to 1 state, 1, I equal to 2 state, 1, blah, 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 blah. It's going to be going on until what? Let's say there are k states, right? So, I mean, the multiplicative factor gi is always going to be there, okay? So then, this is going to be 1, and the denominator is going to be a series of 1s such that, the endpoint is some k, arbitrarily chosen k, and I'm adding 1 how many times? K times, okay? So this is going to be something like gi by k, right? But the fact that my partition function is equal to 1, right, all the way up to k, all the way up to all the k states, right, indicates that all my states are equally accessible. Okay, so this particular statement implies that at t tends to infinity, all energy states are thermally accessible. Right? So we saw one more example, right, by considering the other extreme case as t tend to infinity, that my Boltzmann distribution implies that all energy states are accessible at t tends to infinity. Now this also dispels one more myth. Okay, what is a common myth? We tend to kind of intuitively understand wrongly, in fact. Okay, right, that as t tends to infinity, we are naturally inclined to assume that, oh, the highest energy state is only going to be occupied, correct? But what this particular expression here tells us that is not the case. Okay, so I will dispel a common myth. Note, at t tends to infinity, I'll write it here. Okay, as t tends to infinity, not only the highest energy states are occupied, not only the highest energy states are occupied. What it tells you is that all states are equally likely occupied. Okay, right? So this is a myth which has to be dispelled. Okay, so what did we do so far? By considering the extrema, that is t tends to infinity and t tends to 0 case, we saw that the partition function gives us tremendous molecular information, right? Molecular information about the energy states which could be thermally accessed at any given temperature. So at t tends to infinity, all states are equally likely, and as t tends to 0, only the ground state is going to be likely for us. Okay, I hope the message is clear, right? So this is the significance of this term partition function, and now therefore we see that at moderate temperature, some lying, let's say around room temperature or something, which is routine in terrestrial chemistry, right, we understand that some energy states are going to be occupied. Okay, now you may ask me a natural question: why did we spend so much time with this concept partition function? Why spend close to 2 tutorials, right, on partition function? What is its relevance to astrochemistry in particular? Okay, that is what is going to be the next question now. So this is going to be, because we continued from the previous question in the last tutorial, I'll just call this the first question for today's tutorial. What is the significance, okay, right, the significance of my partition function in astrochemistry? Well, the answer is somewhat obvious, but it has to be clearly presented. Okay, now again, to answer this question, let's continue with the same ideas we used in the last question. Okay, it is that start with t tends to infinity, sorry, t tends to 0. That is my beta tends to infinity. Okay, as t tends to 0, we understand that only the lowest energy states are going to be occupied. Okay, now this t tends to 0 holds particular relevance in astrochemistry, right? What is that? Well, in the dense molecular clouds, the temperature, right, tends to 0. We are talking about temperature less than 20 Kelvin, right? So t tends to 0, which implies that in such cases, right, the chemistry of the molecular clouds, the dense molecular clouds, is dominated by molecular rotations and some vibrational states. Okay, dense molecular clouds, right, the chemistry of the dense molecular clouds, I'm just going to call them DMC. Okay, dense molecular clouds, right, the chemistry of the DMCs dominated, I've written here, dominated by molecular rotations and some vibrations. In other words, electronic states are not going to be that relevant in this case. Okay, rotations and vibrations at very low temperature. Okay, right? So this is one immediate astrochemical significance of the concept of partition function. Likewise, similarly, if you consider, so when t tends to infinity, for the case of astrochemistry, let's say within astrochemical context, let's say our infinity, let's say we define it as 10 to the power 6 Kelvin or 10 to the power 8 Kelvin, etc., etc. That is at very large temperatures, right? All states are accessible. When I say all states, I'm talking about all energy states, which implies that electronically excited states, that is, electronically very high excited. We're not just talking about the first or the second excited state. We're talking about higher excited states. Okay, will also be important. So what the idea of partition function establishes is that at low temperatures, right, at very low temperatures, we're talking about temperatures less than 20 Kelvin or 50 Kelvin, even temperatures ranging in 1 digits, the chemistry is dominated by molecular rotations and vibrations, because though they are the lowest energy possible states, right? Predominantly rotations and some vibrations also. Of course, translations we exclude because they're exceptionally low energy. All right, we shall in fact see in a subsequent lecture that there is something called as a rotational temperature. Okay, that rotational temperature is a measure of the temperature of the system itself at very low temperatures. They range of the order of, say, something like 4 Kelvin or 5 Kelvin or something like that. Okay, right? So you can see that at low temperatures, the chemistry is dominated by molecular rotations and vibrations, whereas at very high temperatures, all kinds of electronic states also need to be taken into account. Okay, but another fact is that just because you take into account the electronic excited states doesn't mean the vibrations and rotations could be ignored. Okay, they're also going to be playing a part along with the electronically excited states. Okay, so this is the relevance of your idea of partition function in astrochemistry. All right, are we clear? Okay, so on that note, I'll proceed to the next question. The next question, right? This was question 1. The next question is going to be question 2. It is that starting from the Boltzmann distribution, that is BD, including the degeneracy. Okay, get an expression for the ratio of the number of molecules present in any two states, assuming local thermal equilibrium. Okay, okay, so this is the question, and so we'll start from the Boltzmann distribution for a system in local thermal equilibrium, considering degeneracy also. So the answer is, say, for some state N1, let's say the degeneracy is G1, and that is given by, this is beta, is equal to how many ever number of states. All right, so this is, let's say, for some state N1. Now let's say for some other state N2, and notice that the summation over here is not just in terms of state but in terms of degenerate states. Okay, so my N2 is going to be given by, let's say, G2, where G2 is the degeneracy of the state N, divided by sigma over I equal to 0, e to the power minus beta EI. Let's say this is equal to Z. Okay, the Z is going to be the same in both the cases, right? So this is going to be page number 11. And so, well, per the question, right, I want this ratio. Let's say, I want N2 by N1 or N1 by N2. Let's say N2 by N1. So my N2 by N1 is therefore going to be G2 by G1, and the denominators are going to be the same, so they get cancelled out. So this shall be first e to the power minus beta times E2 minus E1. So this is going to be therefore written as G2 by G1 times e to the power minus beta times delta E. All right. Now this was the expression that we saw. Let's say, I think in probably lectures 43 or something like that. Okay, we were deriving the Einstein coefficients. Okay, where my delta E is defined as E1 minus E2. We are fine, right? So this is the expression for the ratios of my N2 by N1. Okay, are we all good? Okay, so on that note, we'll call it a day. I'll just summarize what we saw today. We started off by looking at the expression for the partition function at t tends to 0 and t tends to infinity, and in both the cases we saw that the partition function was indeed a measure of the thermally accessible states. As t tends to 0, we saw that the ground state is in the at t tends to 0, it is the ground state that is predominantly occupied, and when expressed in terms of degeneracy, the z naught, that is like z as the value of the partition function as t tends to 0 is equal to g naught, that is the degeneracy of the ground state. And this was followed by our understanding that at very high temperatures, as t tends to infinity, all states are going to be equally likely. We also dispelled a common myth that at very high energy states, the highest energy states are going to be occupied. No, that is not the case. That is wrong. Instead, all energy states are going to be occupied at very high temperatures. This was followed by our understanding that partition function is very relevant in the area of astrochemistry, which is why we spend so much time on it, right? And we saw that the chemistry of the dense molecular clouds at very low temperatures, they are dominated by molecular rotations and vibrations, as the partition function indicates, right? And at very high temperatures, all kinds of crazy electronic states are also going to be important. Okay, we saw that, and finally, we derived an expression for the ratio of two different states, N2 by N1. Okay, right? So this is what we saw. So on this note, we shall end this tutorial, right? I'll see you all in the next class, that is lecture 53. Thank you so much.